Hey guys, Mr. B here, and in this video we're going to be going through Chapter 20, Section 2 on electric current. So in this section we're going to be taking a look at different types of electric current, alternating current and direct current. We'll be taking a look at different types of materials that can conduct electricity, like conductors and insulators. And essentially we're going to be looking at what is electric current and some different properties about it that will affect how it moves, such as resistance and voltage. Okay, so there's a lot of vocab in this section. I would recommend maybe, really focusing on some of those words. I wouldn't say make flashcards per se, but, having a good understanding of what those words mean is going to make it a lot easier to understand concepts later on in this chapter, because I'm going to use these words a lot. And if we don't know what they mean, it's going to be really hard to kind of, stay along and understand what's going on. Anyway, so let's begin here. First off, let's talk about the types of electric current. So electric current is essentially sort of like the flowing of water, okay? So if you think of electric current as water flowing through a pipe, it makes a lot of these concepts a lot easier to understand. So, or think of it like a hose, right? So when you turn on a hose, like outside your house, you're gonna have water flowing continuously through this hose, right? That's a current. Just like in a river, water is flowing downstream and it's constantly moving, so we have a current. An electric current is a continuous flow of electric charge. Now, the electric charge is primarily going to be electrons that are going to be on atoms, okay? And the electrons are essentially jumping from atom to atom to atom as they kind of move in a certain direction. That's what we call an electric current. So this continual flow of electric charge is electric current, just like a water current is. And there's two ways that this flow can move, okay? Now, in a hose, it really only flows in one direction, so it's kind of hard to imagine a hose doing this. But in an electric current, you can have direct current, which means that all of the charge is going in one direction. So this is like a hose, right? You turn the water on and it all goes out the hose that way. That's direct current, okay? Even though it's called direct current, it has nothing to do with like it's going from here to there and it's going like directly there, okay? It means one direction. It's moving in one direction. And then you have alternating current. Now, alternating current's kind of weird, okay? But alternating current is essentially where you have electrons that move this way, and then they move backwards. Then they go forwards, and they go backwards. And then they go forwards and backwards and forwards and backwards. And they essentially will move further this way than this way. So they'll go far, and then a little bit, and then far, and then a little bit, and then far. So they are like inching their way down one direction in particular, but they don't just go all one way. They kind of like go back and forth as they kind of work their way down. Obviously, hoses don't do this, right? If you turn down water for a hose, it's not going to like squirt out and then go back in the hose and then come back out and then go back in the hose. That would be weird. But electric current can do this, okay? So you need to understand that a lot of different types of wiring and stuff that we use when it comes to our lights and buildings aren't all just going to be charges going in one direction down the wire. They can sometimes go back and forth and be alternating current. So let's take a look at where are some examples of direct current versus alternating current in real life, right? What kind of things have direct current? So batteries are a really good example of objects with direct current where the charge will go in one direction. Okay, now the reason why we know that batteries have direct current is because if you put in batteries, let's say in a flashlight or a remote control or something, and you put them in wrong, right? I'm sure all of you guys have done this before. You had to change the batteries out and you put the batteries in and you don't like know which way they go because maybe they're not labeled, and you just like flip it in this way and you try to turn it on and it doesn't work. And you're like, oh, I got to flip it around and put it in that way. That's because the charge has to move a specific direction within that object. And if you don't put the battery in the right orientation, the charge can't flow that way, which means it can't flow at all and it won't turn on. So in a battery, typically the charge is going to go from the positive terminal to the negative terminal, okay? So it'll flow clockwise or counterclockwise. It doesn't really, depending on which way your battery's oriented, but it's going to go from positive to negative, okay? But it only goes in one way. It doesn't turn around and go the other direction, okay? That's direct current. Whereas alternating current is primarily going to be found in power lines or wires that are transporting electricity over long distances. Alternating current, again, is when the current goes one direction, and then it comes back the other way. And then it goes the other direction again, and then it comes back the other way. And the reason why alternating current is primarily going to be found in power lines or essentially like wires or power that's under the ground that travels long ways is because alternating current is a lot easier to transport over long distances. Direct current, like things like batteries, don't go very well over long distances. So, when you have a battery, oftentimes that battery is directly connected to the object it's trying to power, or it's very close by, right? Because it doesn't move very far very easily. Whereas alternating current can travel miles and have no problems, right? Which is good because obviously if we use direct current to power your house, there would need to be a power plant like right outside your home, which would be really smelly and noisy and it wouldn't be very fun to live nearby. Most power plants are not nearby cities. They're usually like miles out and you don't really see them for the most part, but they're pumping electricity through wires and power lines long distances to get to your house or get to your office or your school to make sure that you have electricity for your lights and everything like that, okay? So the advantage for alternating current is it can travel long distances really easily and direct current can't, okay? Just because it's harder to get it to travel a far distance. All right, so other than the types of electric current we have, let's talk about the types of material that can essentially use electric current. So there's two types of material here that we're going to talk about. We have conductors and insulators. So conductors are materials that allow electric charges to flow through them very easily, whereas insulators are materials that don't allow electric charges to flow through them very easily. Now, I'm sure you probably have a pretty good idea of what types of materials are conductors and what types of materials are insulators, but we're going to cover them anyway. Okay, so things that are good at conducting electricity. Metals, right? Most of you probably know that metal is a very good conductor. Now, some metals are better at conducting than other metals. Copper is a very, very good metal at conducting electricity, which is primarily why most wiring is made out of copper. But there are better metals than copper when it comes to conducting electricity. In fact, one of the best metals to conduct electricity is gold. Obviously, the problem with that is that gold is very expensive, so we can't make all of our wires and stuff out of gold. But if you ever get very high-end electronic equipment or any kind of really high-end electronics, you might notice that the plugins or things like that are gold-plated, right? You can look at it and it looks gold. That's because it actually has gold on the surface. Now, the whole thing isn't typically made out of gold because that'd be very expensive, but the very outside layer is coated in gold because it allows electricity to transfer through it a lot better, and you usually get better video quality, you get better audio quality, and just overall, you get a much better electrical device, whereas if you don't use gold, okay? So you might notice that on high-end electronic equipment, you do have gold plating on the outside of a lot of those plugins and things like that. Now, there's a YouTube video here. I'm not going to watch it, but if you want, I can put a link to this in the description of this video, and then you can go watch that YouTube video. It just talks about some different types of materials. So. All right, the other type of material we have are insulators. An opposite of a conductor, an insulator does not allow electric charge to flow through it very easily. So things like this would be like wood, rubber, glass, plastic. Technically, the human body also is not really. I mean, we do conduct electricity, but we're a lot more of an insulator. So either way, materials like insulators are really good at essentially stopping charge from flowing through them. So insulators will come into play when we don't want charges to go through materials. So if you ever look at wires, right, in your house or outside, they're usually going to be coated with some kind of material that is an insulator, like rubber, right, or plastic. That's because if something touches the wire and it's, a conductor, that charge is now going to leave the wire and go into a different object, which is what we don't want. We want it to keep going through the wire to wherever it is we're trying to power. So we'll cover the wires in insulation, which will stop it from being able to get out of the wire and essentially keep the power and the electricity flowing down the wire to where we want it to go. All right, so let's talk about some properties here of electric current that you might not be as familiar with. So one of these things is called resistance. Now, we talked about how electric current is like water flowing through a pipe. And there are sometimes things in the way that will stop that water from going through the pipe, right? So like, let's say maybe there's like some spider webs in your garden hose, or maybe like someone shoved a rock in there, right? Or you take your thumb and you stick it over the front of your water hose and the water, sprays out like this. This is what we call resistance. It is the opposition to movement of a charge through a material. So basically, it's like friction, okay? The more resistance you have, the more difficulty it is for stuff to go through a wire or for like something to go through a material. So All materials have some amount of resistance. Conductors typically have very little resistance because they allow charge to flow through them pretty much unimpeded. Insulators have very high resistance, meaning that there's a lot of friction. It's very difficult for charges to move through the insulator, which is essentially why they don't conduct electricity. Now, resistance is typically measured in a unit called ohms. Okay, it's a strange word here. And it's oftentimes represented by a Greek letter called omega, which again is a very weird symbol you probably have never seen before. So if you see the word ohms or this symbol omega, that is the unit we're going to attach to resistance. Okay, just like meters is a unit that we would attach to a distance or a length, or seconds is a unit that we'd attach to time. Resistance is measured in ohms. Now, there's a couple of different ways that we can change the resistance of a material. Okay, the size of the material in terms of its length, the shape of the material in terms of how wide it is, and its temperature will all affect the resistance. So let's take a look at two examples here, okay? And this is probably best if we imagine that these are roads. So imagine that this first pipe here is like a one-lane road, and it's during rush hour, and you got all these cars that are all trying to go home, and they're all like backed up behind each other, right? And they're all like piled in, and they're all going really slow. Versus this one down here, let's say this is a three-lane freeway, and we've got all of these cars in 3 lanes. Of course, it's rush hour, so they're all backed up, but you know, you got a 3-lane freeway. The wire on the top is going to have more resistance than the wire at the bottom. And that's because when you have only one place, one tube for everything to go down, it all gets crunched up and backed up, and you all got to go really slow as you're all going in single file. Whereas this one down here, although it's all backed up, it's a lot wider. So you essentially have more room for all of these things to go down, and you can get more objects, more charges to go down there at any given time. So thicker wires will have less resistance than thinner wires. Okay, thin wires, of course, since there's less room, you got more friction. Everything's like, backing up into each other. Likewise, the length of the wire will also matter. So if you have a short wire, you have less resistance than a long wire. And this is primarily because a shorter wire, there's less material for the charges to move through until they're out of it. So there's less stuff for them to run into, there's less friction. The longer the wire is, the more friction there's going to be because they have to travel their way through this whole wire. And as they're doing that, there's all this stuff that's getting in their way and slowing them down. More resistance, okay? Lastly, then we have temperature. Temperature also will affect resistance. If you lower the temperature of a material, okay, so inside of every single material, there's atoms, and all these atoms are constantly moving around. Now, on a large scale, you don't see these vibrations because they're very small, okay, but every single material, which is made out of atoms, those atoms are constantly moving, okay, they're vibrating, they're kind of moving in place like this. When you heat them up, those atoms, which maybe are moving like this, normally, as you heat them up, they're going to start moving more and more and more because they're getting more energetic and more energized. And they start going all over the place. That's going to be really hard to work your way through when you got all of these atoms that are bouncing all over, right? Imagine like trying to walk down a hallway and you got 100 people in the hallway and everyone's like running around at full speed and you're just trying to like get your way through and not run into anybody. Really, really difficult, right? You're going to hit people. People are going to hit you. You're going to have to go really slow as you're like dodging and weaving people to not get run into. Versus a cold temperature, when you lower the temperature of a material, rather than them vibrating like this, as they get colder, they slow down until eventually they're either not moving or they're moving very, very, very little. In which case, it's a lot easier to move your way through something when you don't have to worry about running into stuff, right? That'd be like, again, you're walking down a hallway and there's 100 people, but everyone's standing in place. They're not going anywhere. Well, now it's pretty easy to not hit anyone, so I can just walk around them, right? Same premise, okay? So large temperatures, you have all this movement, you have a lot of resistance, a lot of friction, whereas cold temperatures, you have very little movement, in which case you have very low resistance, and it's easy to move through because there's nothing that you're going to run into, okay? It's the best analogy I can give you. All right, so last stuff here we're going to talk about is voltage. So what is voltage? Now, this is something that a lot of people kind of are scared of, but they don't truly understand what it means. All right, so I'm sure you've seen signs that says like high voltage, right? Danger, be careful. When it comes to electricity, voltage is like how much pressure there is pushing on the electrons to push them through the wire, okay? Or it's like water pressure. So imagine that you have a hose, again, like outside your house, and you just barely turn the water on, right? It starts to trickle out of the hose, but it's not like really flowing well. That's going to have low voltage, low water pressure. Okay, the pressure of the water is very low. It's not really shooting out very strong. Versus if you take that and you crank it up to the max, right? And the water's like just shooting out of the hose. Now you have very high water pressure. That is high voltage. Okay, there's a lot of pressure pushing the water through the hose. Same thing when it comes to electric charges. Low voltage means that the charges are not getting pushed very hard through the material, and they're essentially moving pretty slow. High voltage means that the charges are getting pushed really hard and they're moving really quickly through the material, and that essentially can be dangerous because high voltage usually means high current. And the current is the part that actually is dangerous. It's not the voltage part. It is possible to have a large voltage but a low current, in which case you actually won't get injured at all. You'll be completely fine. But usually high voltage means high current. Okay, so electric current will flow. Okay, so things will flow through material because there is voltage that is pushing the charges through the material. Okay, and the reason why voltage is able to push things is because there's an electric potential difference. Means there's an energy difference. At one end, there's usually high energy, and at the other end, there's usually low energy. And things always want to go from high energy to low energy. And the bigger the difference is between the high energy and the low energy, the more force there's going to be to push these things from high to low. So imagine it's like a hill, okay? You've got a hill that's this tall over here, and down here it's this low. If you take a ball and you drop it down the hill and it's really steep, it's going to roll really fast. Versus, let's say the hill's maybe only like a kind of like a little incline. Well, now if you drop a ball, it's going to roll, but it's going to roll a lot slower, right? Because there's not as big of a difference between the high point and the low point. Voltage is essentially a difference in energy. You have a high energy point and a low energy point, and the bigger the difference, the more force there's going to be to push those things down the hill, okay? Or from high energy to low energy. Okay, anyway, so this again is what we call electric potential or electric potential difference. It's voltage. It's just another way of saying the same thing, okay? It's voltage. So now when a charged particle again moves from one place to another, there's going to be some force pushing it from one place to the other. And the difference in potential is typically generated by the charge's electric field. This was learned about in the first section of this video, right? Electric field is the effect that charge has on other charges around it. So the bigger the difference is in those two places in this electric field, the more voltage there is and the more force that charge is going to feel, and typically the faster it's going to move. Okay, we measure this in volts, which of course is a unit that we're all probably familiar with. Now, what produces voltage, right? So how do create a voltage? Well, there's a couple of different ways, but the main ways are batteries. Okay, batteries, on one end of the battery, you have high energy, on the other end, you have low energy, and there's a voltage or an energy difference. And the charges can't move through the battery. There's usually something in there that stops them. So the only way for them to go from the high energy point to the low energy point is you have to connect the two on the outsides by a wire or something, and then the charges can flow from the battery through the wire, power whatever it is you're trying to power, and then get to the other side, and then they're good to go, okay? So batteries, solar cells, generators, all of these things will produce high energy, and then you connect that thing to something that's low energy, and the charge will automatically flow from that high energy to the low energy, and now you have a way to power something. You have a power source or a voltage source. All right, so these three terms, current, voltage, resistance, can all be related in something called Ohm's Law. So Ohm's Law is an equation. It basically tells us that the voltage of an object will be equal to its current, which is measured in, or its current, which is given the symbol I, okay, not A. So its voltage is equal to, and let's make this big enough that we can actually see it all. So apologize that this is not big enough to begin with. There you go. So voltage is equal to current times R, which is resistance. Okay. Oh gosh. Why does this not want to work? There we go. Okay. And this is resistance. So Ohm's law basically says that the voltage in a circuit is equal to the current in that circuit times the resistance. Remember that voltage is measured in volts. Current is measured in amps, okay, or amperes, which you probably have heard that term before, amps, but that is measuring current. And of course, resistance is measured in ohms, or, that's where Ohm's law comes from. So if we increase the voltage in a circuit, we will essentially increase the current, okay? So if you increase voltage, you're increasing the amount of force that's pushing on the charges, which will make them go faster. And the more charges you have flowing through a material, the larger current you have, right? Just like in a river, if you have a very high current, that usually means that if you step into it, that river is going to sweep you downstream really quickly, and it can be very dangerous for you. Same premise here. If you have a very high voltage, there's a lot of force pushing on the electrons, which basically is going to mean that they're moving very quickly, and you have a very high current, which can be very dangerous. Likewise, if you increase the resistance, that will decrease the current. So that's like basically taking a river and shoving a bunch of rocks and stuff in the river to make like a big rock wall. Well, now the current's going to slow down a lot, because as it tries to go down river, it's going to hit all these rocks and it's going to slow down because there's all this friction now stopping it, and you'll lower the current, okay? So increasing voltage will increase the current. Increasing resistance will decrease the current, okay? All right. Anyway, so that is it for this section. I know that was a bit long and there's a lot of information. So if you have any questions, please make sure that you reach out and ask, okay? Again, you can email me, you can chat with me in class. If you want some practice, we can always do a one-on-one over Google Meet or something, but make sure that you get those questions answered. All right, guys, that's it for this section. I'm Mr. B. See you in the next one. Bye.